A very good afternoon to everybody. Uh, Thank you very much for this opportunity, and I thank Bharati Dasan University, the senior professors, and Sabari for giving me this award. So I will talk about, hopefully in next 1 hour, some basics which Reggie has covered in great detail, some aspects of the materials, nonlinear optical materials, and some applications of these materials in various fields. So I'm from Akraham University of Hyderabad, which is a DRDO Center of Excellence created in 2005. So at the outset, I would like to thank the organizers. I would like to thank all the funding agencies who have been generous in providing us money over the last 15 years. I also thank my students who have been the workforce since I joined IIT Guwahati, my past students, present students, postdocs, and several collaborators, including Sabri and Reggie, within and outside our university. And most of the slides I've collected from my friends, the World Wide Web, and colleagues for the materials used in presentation. I would like to acknowledge them. So a very famous statement by a pioneer in nonlinear optics, Yonren Shen, who has a good nonlinear optics book, he said that physics would be dull and life most unfulfilling if all physical phenomena around us were linear. Fortunately, we are living in a nonlinear world. While linearization beautifies physics, nonlinearity provides the excitement in physics. So it's a beautiful statement. So what I will cover in this talk is, again, a little bit of nonlinear optics, what Reggie covered. I will not go into that, maybe a little bit extra of what is left out by Reggie. Some basics of second, third order nonlinear optics, processes involved, mechanisms involved, what are the processes responsible for these nonlinearities, what are the various materials which we investigated, which others are investigating. It's a huge field, so I'll try to give a flavor of the materials and the mechanisms. Some applications of these third order, second order nonlinear coefficients, and sometimes third order cross sections, various challenges, scope, and finally conclude. So can the optical properties of a medium depend on the intensity of the radiation with which it interacts? The answer is yes, as Reggie has already pointed out. For a strong field, you will see a nonlinear interaction of the matter with the laser field. Usually electric field strength of atomic interatomic fields are 10 power 7 to 10 power 10 volt per meter. Now field strength of conventional light like tube light, however powerful mercury vapor lamp or lamp you take, they are simply of the order of 10 power 5. So they don't really change the interaction of light with the interatomic fields. It does not perturb the interatomic fields. So low intensity light will not be able to affect the atomic fields to the extent of changing optical parameters. Now with the laser being developed and discovered in 1960s, the high degree of coherence as well as intensity of these laser pulses made it possible to have extremely high spatial concentration of light power when you focus it using a lens. So in certain lasers, it's possible to generate few hundred gigawatt of peak power pulses. Now this has gone to terawatt and petawatt. So we have 1 petawatt laser in RRCAT and 1 petawatt laser coming up in TF for Hyderabad, which lasts only for a few tenths of a femtoseconds. So this we have already discussed. The electric field polarizes the atom when you put an atom in the electric field. If the field is not too strong, the amount of induced dipole can be small. It can be assumed to directly proportional to the electric field. A small field will displace the charges a little bit, and like your spring mass spring model, a small oscillation, a small displacement will make it simple harmonic oscillations. So it is the large field will displace them further and in proportion to the field unless the displacement gets too large. So we have seen this polarization is linearly proportional to the electric field, and the constant we define is called the chi, and this is the basic electric susceptibility of the dielectric. These are the slides I've taken from Professor Rick Trebino lecture notes, which are very beautiful, which are easy to download, free to download, and I request all the students who are interested in NLO to download this. If you plot the energy versus position, this is how the potential looks like around the nucleus. The potential gets at far away from the nucleus, it goes out, it gets more flatter at the infinity region, which means far away from the nucleus. So the electron motion can easily go nonlinear when you take the go away from the nucleus. The electron's motion will no more be a sine wave, it will depart from the sine wave. So why does nonlinear optical effects occur? In normal nonlinear optics, light interacts with a matter, in this case molecule, and you have emitted wave. There's no change input wave and output wave. So these molecules, the atoms vibrates and then they emit their own light, which interferes with the original light wave. So this can be imagined in terms of energy level size. You have input light taking the electrons from the ground state to the excited state, and then they come back to the ground state. So there is no nonlinearity here. But when your light is strong enough, irradiance is high enough, or the peak intensity is high enough, then the molecules are excited to the higher levels. And then what you have is emission, which is no more linear in intensity, it depends non-linearly on intensity. In this case, what you have an input wave, an emitted wave, which is of a different color now. In the earlier case, the color did not change. In this case, color changes or the frequency changes. This is called nonlinear frequency conversion. As I said, a mass attached to a spring, when you have a small displacement, you get a simple harmonic motion. This is the equation which governs this damping term and the driving term. For linear polarization, the potential is more or less parabolic. It looks like this. When you have second order terms, then what you see is that potential gets distorted, and when you have third order terms, it gets completely distorted. These are the common terms which you've already seen. So the polarization can be expressed as a linear susceptibility tensor. In this case, we are writing chi ij, and then second order susceptibility tensor chi ijk, ej and ek, and chi ijkl, third order nonlinear susceptibility tensor ej ekal. So these chi's are all tensors now. E's are electric fields, so chi's will be tensors. This is rank 3 tensor. Second order chi2 is a rank 3 tensor. Chi3 is a rank 4 tensor. So therefore, chi4 will have about 81 elements. Chi3 will have 27 elements inside that tensor. This already we have seen. Suppose you consider the first solution, sinusoidal solution for the electric field. When you plug it in your polarization, what you get is extra terms at 2 omega and 3 omega, which means that these are the harmonics of your fundamental second harmonic and third harmonic. The presence of new frequency component due to the nonlinear polarization of the medium. The magnitude of the term in 2 omega approaches to the first term when the electric field is about 10 power 6 volt per meter. So if you convert this electric field in terms of intensity, light intensity, it will be about 10 power 9 watt per centimeter square, which we can achieve using a simple NDR laser focused by a small lens. So while the electric fields and power density of sunlight are very, very small to induce any nonlinearity. So as I said, 1961, the first economic generation was observed by Franken in KDP. And then that signified the birth of nonlinear optics, and the rest is history. So I'll skip this introduction again. So you see that we have chi2 and chi3 now. And when you put in electric field, which is a sum of sines and cosines, what you get is terms which will have second harmonic terms, 2 omega terms, whereas you're pumping in with only omega term. As Reggie pointed out, there will be symmetry issues in second harmonic generation. For example, if you look at the signal, second harmonic, which we are generating using a second harmonic crystal, this is fundamental. The electric field is given by E of t. And here you get 2 omega, which is E2 of t. And if you imagine inverting the space, the E of t goes to minus E of t, and E of signal will go to minus E of signal. However, the crystal is medium is isotropic. Therefore, chi2 will not change its sign. So E minus E of signal t when you are inverting the space is proportional to chi2 minus E of t square. So this minus gets cancelled out. So what you get is minus E of signal t will be chi2 E of xt, which is equal to signal t. And this conditions is valid only when your chi2 is 0. Otherwise, you cannot have a minus term here and a plus term here. So this necessitates that chi2 is 0 for a media with inversion symmetry. So the lowest nonlinearity you see is the third order nonlinearity in inversion symmetry materials. And when you take, for example, expand this thing using two frequencies now, omega 1 and omega 2. So instead of one frequency, you're putting in two frequencies, then you see various and simple mathematics. You square this term, what you get is omega 1 to a second harmonic of omega 2, some frequency, difference frequency, as well as the optical rectification. Now, do they occur all simultaneously? No, they do. It is possible for them to occur, but then which one will dominate? That is determined by the, and what determines the efficiency of a particular process is determined by the phase matching condition. You can have in principle n wave mixing process. You can see here, for example, omega 1, omega 2, omega 3 taking the system from ground to the excited state. Then there are transitions, again the excitations. Then you have a final omega signal, frequency emitted signal. This is, for example, a n wave mixing process. When I say a dashed line here, these are all virtual levels. It can be real levels also in some cases. So this is a process which describes a five-way mixing process, E1, E2, E3, E4, because E4 is in this direction, therefore you get a E4 star here. So you can write down this kind of a polarization terms. In all these processes, the energy is always conserved. So you cannot destroy energy. Therefore, any nonlinear process, energy is conserved. That gives rise to this kind of equation where omega 1 plus omega 2 plus omega 3 minus omega 4 plus omega 5 is omega 0, which is the incident, which is a resultant photon here. Photon momentum also must be conserved. That gives another condition. And both of these together is called as a phase matching condition. You need to satisfy both these conditions together. That's why it's called a phase matching condition. We have seen these indicatrix where you have materials with different refractive indices in different directions. So you can choose those materials. For example, you can have a spherical highly symmetric cubic crystals, where example you have only one refractive index, and this is how the equation looks like. When you go to uniaxial crystals, for example, crystals with single optic axis, which have different symmetries, then this is the equation we use. And when you have biaxial crystals, orthorhombic, monoclinic, or triclinic, then this is the equation where you have different refractive indices in different directions. And you can also find out which one is ordinary and which one is the extraordinary wave. So as a function of theta, for example, this is direction of the propagation. You can calculate the E wave propagating along a direction as at an angle theta, right? So the two polarization directions are then OA and OB. So you can write down an equation for this as a function of theta. Now you vary this theta, then you can vary the condition for your any and NO. That's how you do the phase matching depending on your input polarization as well as the input wavelength, which you want to convert into second harmonic. This Reggie has discussed already. In normal materials, it's not possible to match the refractive index of 2 omega and the refractive index of omega. You see, this is much lower here and much higher here. So in normal materials, it's not possible, but in other materials, in a special case of crystals, you'll be able to match this. For example, the refractive index of lambda 2, when it is in Na, is matching with the refractive index of NO at lambda 1. So this is your one of them is a fundamental, one of them is harmonic. Both of the refractive index matches as both of them travel together. Therefore, you have a very good conversion efficiency or a good phase matching. So this I will skip again. This is the equation which Reggie has already discussed. You get the sinc function, and when delta k is 0, you have the maximum intensity of the third wave, or this is some frequency. This can be used for second harmonic also. In this case, I'm talking of I3. So what are the different techniques for measuring? One is the most famous method called the Kush-Perry powder method. Well, then you have hyper-Rayleigh scattering. Then you also have in some cases of liquids, we can do electric field-induced second harmonic generation. So when you do the actual mathematics, Chi2 is not easy to work with. So people have found a way to reduce the dimensions, and then instead of 27 elements of Chi2, you can reduce it to maybe less number using what we call as a D effective. So whenever we talk of second order nonlinear material, we always talk not of Chi2 value, we talk of D effective. So any crystal you talk about, we look at the D effective, which is equivalent to a second order nonlinear optical coefficient. And crystal symmetry plays an important role in second order nonlinear optics. D effective is strong, D effective is desirable. Of course, you need to have good transparency because they need to, both fundamental second harmonic need to come out of the crystal. If you have a high damage threshold, it should not get damaged when you put in too much of photons. When there are materials with strong D effective, for example, gallium arsenide, but the phase matching is not possible, then people have come up with artificial phase matching techniques. I'll discuss some of them in this one. For third order measurements, you have the Z-scan, you have the degenerate foam mixing, and the third harmonic generation. These are the three most popular techniques for measuring Chi3. You know, Chi3 has both real part as well as the imaginary part. The imaginary part is related to the nonlinear absorption beta here, whereas the real part is related to the nonlinear refractive index. So once you calculate your N2 and beta, you can calculate the real imaginary parts and the total chi3. So your z-scan will give you the magnitude of chi3, but it will not give you the time response of the chi3. How fast is this chi3 responding? For that, one need to do a time resolved degenerate 4-way mixing so that you get the how one is how strong is the nonlinearity, and second is how fast is the matter responding to the laser. So how fast is the nonlinear response? So these two techniques combined will give you real part, imaginary part, total magnitude, as well as the time response. I will show you some data from our own lab. So nonlinear absorption can be 2 photon, 3 photon, 4 photon, 5 photon. I will show you samples which can also show 10 photon absorption. This already we have seen in Raji's talk. So as I said, now we are talking of D effective in second order polarization term. It's a reduced term, reduced notation. So for example, BBO, instead of 27 elements of Chi2, what we write is only DIL. This will have about only 18 elements. Now all these 18 elements will define the nonlinearity of the BBO, and among them, because of the symmetry conditions, most of them are zero. Only few coefficients are remaining. So once you know these coefficients, then we can identify what is the direction in which you can send your fundamental and then look at the second harmonic. So you get different phase matching conditions. So there are two different types of phase matching conditions. Phase matching condition 1, 2, and 3. I'm not going into that. So depending on the crystal cut, you will be accessing different nonlinear coefficients of this. So one needs to identify what are the magnitudes of these, which direction when you put in the beam, you will access these coefficients, then you can get a very good conversion efficiency. So the efficiency is proportional to this term, as you see, where D effective is the coupling parameter. How do you increase the overall conversion efficiency? Look for a strong D effective material. And you can also increase the length of the crystal, but then you cannot continuously go on increasing the length. Then when you are using pulse lasers, then your group velocity mismatch occurs. So your fundamental second harmonic differences between their group velocity, that will kill the generation of nonlinear generation of the harmonics. You can increase the power density, but then it is limited by your damage threshold. Suppose if there are third order effects undesired, then that goes into third order. Power is not converted into a harmonic generation. Try to get delta K as close to zero as possible, then you have a maximum conversion efficiency. And you also have angular acceptance and spectral acceptance, temperature acceptance. These are minor issues. Limit Volkoff limits the overlap between tightly focused fields. So focusing also is an issue. One need to optimize the focusing. One need to optimize the group velocity mismatch also. So these are the various parameters which will influence the different crystal parameters. Okay. So for example, the repetition rate will determine how is the damage threshold. Beam size will determine the crystal size as well as the Volkoff angle. Pulse duration also will determine what is the thickness of the crystal. For example, if you want to do conversion with short laser pulses, you always go for a thin crystals, less than 1 millimeter, less than half a millimeter, about 100 microns. In some cases, you may have to go even thinner samples so that the conversion is maximum. There will always be conversion, but the output coming out depends on all these factors. The easiest way to increase the efficiency is to increase the power, but there is possibility of damaging. So the damage threshold, what does it depend on? How good is the quality of your crystal? What is the features of your pulse laser? How much is the peak intensity? What is the pulse duration? What is the lambda input wavelength? Spatial beam profile also affects your conversion. How much is crystal surface occupied, repetition rate, total number of pulses, atmosphere, and coatings on the surface. All these things will determine the conversion efficiency. Damages can be surface damage if there are defects or impurities on the surface, or volume damage inside the crystal. There could be self-focusing third order nonlinear effects coming in, nonlinear absorption effects coming in, or Raman scattering. So all these things will help you to design the crystal for a particular frequency conversion process. This we have seen already, the first one, and as Reggie pointed out, the weak spot was removed by overzealous editor who thought it was a speck of dirt. Why is harmonic generation important? For example, this is a very large crystal developed at Lawrence Livermore National Laboratory. These crystals have conversion efficiency about 80%, which means 100 photons of fundamental are converted into 80 of second harmonic. This is how the schematic of the fusion experiments are being done at National Laboratory in the USA. Just now I've checked this. they focus about 192 laser beams into a tiny area which contains this tiny deuterium tritium filled capsule. So this, they are expecting to get more energy out of this. And in the nanoseconds that followed, the capsule imploded and released a neutron yield of this much, or approximately 8,000 joules of neutron energy, which is a record actually. This month only they have reported this record for cryogenic implosions. So 192 beams, these are ND glass laser is used. They deliver up to 1.8 megajoule, which means 1.8 to 10 power 6 joules of total energy, 500 terawatt of peak power at the third harmonic view. That's why you see all this blue color, 351 nanometers, which is converted from the fundamental of 1053. So these are the experiments which are going on at present in the US, and for this you need this third harmonic generation. You need very large crystals, and the whole crystal growth is a booming area in our country especially. So a lot of care needs to be taken when you grow these kind of large dimension crystals. Some of the nonlinear crystals and then their coefficients, as I said, you always talk of D effective or D always expressed in picometer per volt. These are for normal crystals: silver gallium selenide, silver gallium sulfide, beta barium borate, which is very common, cadmium germanium arsenide. You see, for some of them, you see the D coefficient is very strong, 235. So if you can use these crystals, then your conversion efficiency will be much, much higher. These are normal lithium niobate, lithium iodate, and quartz. Quartz, you see, the D coefficient is much, much smaller. You have crystals in the visible region: KDP, KTP, BBO, LBO, lithium niobate, UV crystals. You have KBBF, RBBF, CLBO, YAV, which go into all the way to 150 nanometers. So this graph shows you various UV-based crystals, which means you want to convert your frequency to extreme UV 150 to 400 nanometers. Then one need to use this kind of a crystal because they have transparency in that particular region. Also, they have good analog coefficient. These are various crystals which shows the transparency. LBO has large transparency up to 2 microns, silver gallium selenide up to 8 microns. So if you want to work with a nonlinear conversion 2 to 8 microns, you need to go for this kind of silver gallium sulfide or gallium selenide or lithium indium sulfide, which has transparency up to 9 microns. So various crystals are there. These are routinely grown now. These are commercially available. So you can choose any crystal which you want. You can specify the cut angle, you can specify the thickness, and you can specify the coatings. You'll get your crystal. Some more data sheets are found out: infrared crystal, zinc germanium phosphide, silver gallium sulfide, silver gallium selenide. So for example, in IROPOs, you find most of these crystals. And if you are looking at terahertz generation, then you need to look at zinc germanium phosphide or DAS crystal, which is an organic crystal. So these are all the various coefficients which are which can be accessed at this particular wavelength. So when you mention D coefficient, you should also mention what is a wavelength. So D coefficients vary with the wavelength. A very useful software, it's free to download. It's called the SNL software, developed by this gentleman, Arlie Smith, where you have this nice interface and you can just select the crystals, you can just select the nonlinear optical process, and you can find out what is a phase matching condition. You can find out what is dispersion. A lot of calculations can be done using simple entering. For example, you want to do a OPO base. You can mention what is your input, what is your output required. It will tell you what crystal you need to use. If you use a particular crystal, what will be the output. It's a very beautiful software. I can suggest all of you to download this. It's very easy to use and very free to download. They are upgrading it every time. So I use it most of the time. This will tell you exactly, for example, as a function of internal angle, what will be the wavelength generated for CLBO crystal, type 2 phase matching, and 350 nanometer pump. You can see the wavelengths generated for signal and idler and the polarization. So very useful software. For measuring it, one of the major useful techniques is powder second harmonic generation called Kurtz-Berry powder SHG method, developed by these two gentlemen. This is the original paper which appeared in 1968. What they simply do is you take a Q-switch laser, you focus it onto a sample powder here, collect the emission here, and then you change the size of the powder. And then when you see, if you see this kind of a behavior as a crystallite size varies, particle size varies, if it saturates, then we clearly say that the material is phase matchable. So you can always start with bottom up, measure, make the powder. You need not grow the crystal in first place. If you have a new material, do the powder SHG, see if this kind of behavior is observed, then you can grow a large crystal. So you need not grow the large crystal and then say whether it is phase matchable or not. So this technique that way is very popular. And always you measure with reference to a known sample, for example, urea. You measure the intensity with respect to urea and also say what is the efficiency with respect to urea or KDP. And you can tell that it is 2 times or 3 times or 4 times more than the standard material. In liquids, for example, some liquids have good nonlinearities, but they are not, if they are symmetric, then you do not see this chi2. Therefore, what we do is we apply a strong electric field of the order of few kilovolts, and then that induces non-symmetry, and therefore you can still see the second harmonic generation. And there are a lot of organic liquids which will work in this fashion. So my own group, my junior Srinivas worked on this. We develop this cell which for holding the material, nonlinear optical material, and then apply a large electric field. And in the presence of electric field, you start seeing second harmonic generation. When there is no phase matching, then what is the case? For example, D14 of 170 picometer per volt. These are gallium arsenide. I'm talking about gallium arsenide. Semiconductors are very easy to work with. They have large nonlinear coefficients. At 2 microns, it's 170 picometer per volt, and a very good figure of merit, which is d square by n cube, which is lithium niobate is very standard second order nonlinear material, but it is 10 times more. It has brought transparency, high laser damage threshold. It has integrability with your laser sources or detectors. You can make a full system or a device out of it. Room temperature operation, but there is no birefringence. So there is no dual refractive index. So what do we do? Then we induce what we call as birefringence phase matching or quasi-phase matching or modal phase matching. These are artificial techniques to induce the phase matching. So what we do is we make this kind of a waveguide structure using different growth conditions. And when you look at the refractive index of the TE mode and the refractive index of the TM mode, they have different behavior. The TE-TM waves experience different refractive indices at the interfaces for tangential and normal field. So the strong refractive index contrast. So what we do is we oxidize certain portion in this one. It becomes aluminum oxide. Aluminum oxide has a refractive index of only 1.6, whereas gallium arsenide, this kind of stack kind of structures, they have refractive index more than 3.5. So that refractive index difference helps us in creating what we call as a form birefringence. That helps us in creating the phase matching. Another way is to invert the polarity of the material. For example, Reggie told that this oscillation you see in materials, what we can do is when you reach this point, you invert the sign of this material, then it grows like this. And again, it will grow as per this. When it comes on here, reverse the sign. This is very common in lithium niobate. It's called periodically poled lithium niobate, lithium iodate, lithium tantalate. It's very well used. To use periodic structure to generate an effective phase mismatch so that you have the actual delta K process plus you induce delta K quasi-phase matching, which results in a close to zero value. Therefore, you will have much efficient process. So instead of this one, when you invert these domains, we call it as domains in lithium niobate, you can get this kind of a, you may not get delta K equal to zero kind of behavior like in bulk crystals, but you get reasonably good efficiency when you take large, long crystals. So this is for materials like lithium tantalate or gallium arsenide. So ability to phase match any frequencies in the transparency range, for example, 15 microns, 10 microns, 7 microns, normal material lithium niobate, those crystals will not work. Therefore, these crystals will help us in achieving this kind of a conversion. We can access the largest coefficient, for example, D33 in lithium niobate. So this is a third order quasi-phase matching, and every third peak we are inverting it, or every second peak you invert, or every first peak you invert. Then you get first order quasi-phase matching is more efficient compared to other one. This is a perfect phase matching condition. Again, this requires a lot of MBE kind of machines, but then you can create in gallium arsenide, you can create in materials which can be directly integrated with your pump lasers or your detectors. You can make a device on a simple chip. So we demonstrated QPM SOG when I was doing my postdoc in St. Andrews. So we do domain disordering, quantum well intermixing, or we do ion implantation. We put in some heavy ions and then you change the optical properties of these periods. When you change this periodically, then you can achieve this kind of a quasi-phase matching. and then you still get very good conversion efficiency for your harmonic generation. Orientation pattern, gallium arsenide is a new material. Orientation pattern, gallium phosphide is another new material, where they change the orientation of this gallium arsenide by lithographic process. And when you have this kind of a change, periodic change in your nonlinearity, then you can access the largest nonlinearity of 100 picometer per volt, and you still get a decent conversion efficiency. Now we are talking of very small devices here. Now this is about few millimeter long. You don't need thick crystals. You need very small devices here. So another way to achieve the phase matching is called modal phase matching. So when you have this kind of rich kind of waveguides, again, I'll not go into the details of making this. The refractive index varies for the fundamental as well as the second harmonic. So it is possible to phase match a lower order fundamental mode with a higher order second harmonic mode. So your fundamental will be in the lower order mode, and second harmonic will be in the higher order mode. So these have different modes, like in your fiber, they have different modes. So we can make sure that the fundamental is in lower order mode and harmonic generation is in the higher order mode. Therefore, we can achieve good phase matching. Therefore, we can achieve good conversion efficiency. So here we show this is a fundamental, and this is a I'm showing second harmonic on this and fundamental on this. You get a good conversion efficiency of this fundamental 1.55 micron to 0.75 micron. So artificial phase matching is also possible in these kind of materials, and it is very attractive now. So we come to the third order nonlinear optics part now. We have seen this part. I'll skip this. So we have also seen this. So what are the common third order nonlinear phenomena? Third harmonic generation, then you have induced grating, then you have four-way mixing, then you have the nonlinear refractive index N2, or the self-focusing, self-phase modulation, supercontinuum. All these form a group of third order nonlinear optical phenomena. So when you have all frequencies as the same, then what we call it as a degenerate wave mixing. So here all three input frequencies are same. You have 1, 2, 3, and 4. Then this is called as a degenerate four-way mixing, or you have 1, omega 2, omega 3, omega 4. Then you have a non-degenerate four-way mixing. Again, the phase matching condition in this case is K1 minus K2 plus K3. So degenerate four-way mixing gives rise to an amazing variety of interesting effects. Some of them include self-phase modulation, self-focusing. Okay, I'll skip some more text part. Now we come to the most important aspect of the real part of Chi3. And when you expand this total polarization in terms of linear polarization and the nonlinear polarization, and rewrite it in terms of the linear refractive index and the effective refractive index, what we get is a term which looks like this. N effective is N0, which is the linear refractive index, plus the nonlinear term. We call this modulus of amplitude square is your intensity. Therefore, we call this as N2, N2I. So N2 can be positive or negative. Therefore, your N effective can be N0 plus N2I or N0 minus N2I. So depending on the I, this whole term will be comparable to this. If I is too small, this whole term is very small. Therefore, it more or less is close to the N0. So this is an intensity dependent nonlinear refractive index. Based on the intensity and the magnitude of N2, your N effective will change, and that gives rise to exotic phenomena. The change in refractive index of the material in respect to electric field is known as optical Kerr effect. This was discovered by John Kerr, a Scottish physicist, way back in 1875. So when you write down this for a Gaussian beam, when you write down this, the N effective is N0 plus N2I in terms of Gaussian beam, then what we get is the phase delay was the radial coordinate will be something like this. It will be constant minus a term. So this is what a lens looks like. So the radial phase varies as a function of if you look at this, you can understand. This is how normal lens look like. This is a normal wavefront. When it passes through this lens, it gets focused to this point. A lens is a lens because the phase delay seen by the beam is varies quadratically in x. So it more or less it's x square here. Similarly, if you have a nonlinear material, you need not have a convex surface. You need to have a simple plane surface. Even then, because n of x varies as x square, the whole thing will act like a lens. Depending on n2 is positive or negative, this beam will get focused or defocused. That's what is in your Z-scan experiment. Your sample acts like a lens. Either it is a positive lens or a negative lens. So low intensities, nothing will happen, whereas at higher intensities, it behaves like a lens and it can focus or defocus. That's what happens in your Tice-Sapphire oscillator. Your Tice-Sapphire medium itself, when exposed to high intensity laser pulses, it will try to self-focus, and then you will have the mode locking taking place. So the concept of a Tice-Sapphire laser works on this self-focusing effect because of the input beam, intense input beam self-focusing inside the medium. These are some of the materials for third order nonlinearities. So Chi3s and N2s, usually N2 is centimeter square per watt. Chi3 is in ESU for all glasses, polymers, nanoparticles. This is very limited. This is from the Boyd book, very limited. Now there are more than thousands of materials which are reported daily basis, and their magnitudes will keep on changing. Now, what are the processes which give rise to change in the nonlinear refractive index? What is electronic polarization? Which means the charge distribution of the electrons. When the electric external field is applied, these charges get redistributed. That is called as electronic polarization. That is the quickest in terms of time. Molecular, this usually happens in the femtosecond time domain. Then you have molecular reorder. For example, if you have CS2 molecule or CO2 molecule, then these molecules tend to align in the due to the induced dipole in the presence of the field. This usually happens in the picosecond time scales. Electrorestriction, density change by optical field, saturated absorption, intensity dependent absorption. Thermal effects are much slower in the nanosecond to microsecond to millisecond time scales. Photorefractive index, because of distribution of the electrons and holes, the refractive index change due to local field. It forms like a grating inside, and then there will be periodic modulation of the refractive index. So each one of them will have a different magnitude. The magnitude of this is usually small. Magnitude of thermal effects is much larger, but the response is slower, whereas the response is faster. So ideally for device applications, we want strong electronic charge, electronic polarization as well as fast electronic polarization. So various materials are discovered. This is again, I will skip this part. We have gone through this. This is a typical ZISCAN experiment in our lab. So you focus it through a lens, you go through the sample, align it, we move the sample across using a stepper motor and a motion controller. Everything is automated. You collect the light in the presence of aperture and in the absence of aperture. You collect it and put it into a lock-in amplifier, and the whole thing is automated. So you get a simple transmission curve. Again, I'll skip this. As Professor Sheikh Bhai said, you can have second order or third order. In this case, this is beta, this is gamma, this is 3 photon, this is 2 photon absorption. You can have multiple other orders also. This is a four-way mixing. One form of four-way mixing is called the boxcar geometry, where you put in 3 beams in the 3 corners of the box. It mixes in the sample and gives you a signal in the 4th corner of the box. This is a very specialized experiment, and it gives you the magnitude of the Chi3 as well as the time response of the Chi3. This is how we aligned it in our lab. You can see these are the 3 input beams, and this is the K4 is the signal. And what you see in between these 2 beams is autocorrelation of these 2 beams. So you see a second harmonic here, second harmonic here, second harmonic here. This is in a simple BBO crystal. You can align it. And once you have aligned, you take out the BBO crystal, you put in your unknown sample, and then you can measure the magnitude of K4. And one of them have to be on a translation stage. One need to delay the beams, one of the beams or both the beams. Then you can study the time response of this particular material using this exotic technique. Various forms of degenerate four-way mixing, forward DFWM, phase conjugate DFWM, boxcar DFWM. So optical care gate kind of thing, which Professor Van Stryland will talk about today evening in great detail. Then we also need to know, when you do a Z-scan, we need to know where is the nonlinearity coming from. So for that, one needs to, if you want to understand completely, one needs to know the excited state dynamics, or we do what we call as transient absorption spectroscopy. You have a pump beam which will excite the sample here. Then you have delayed probe beam. That beam comes and interrogates this excited state sample, and then we record the transmission of this probe in the presence of pump and in the absence of pump, and then from that we can calculate. So if you look at organic molecules, that highly complicated energy level diagram. So you have a singlet states, which are the electronic states. So the transition can go from here to here or here. Then once they are excited, they come down by non-radiative ways or radiative ways it can come down, it goes to the triplet states, or when it comes down from the triplet state, we call it as phosphorescence. When it comes down from singlet state, we call it as fluorescence. These Wrigley lines are called the non-radiative transitions, which means the energy is transferred to the surroundings rather than in terms of light. So you have light-based emission, you have non-radiative transition. So a lot of processes are possible. So again, I'll skip the theory for this scan. So we start with some new materials. These are what we call as perforins and phthalocyanins. These are large organic molecules where you have large number of pi electrons, what we call as loosely bound electrons. Sigma electrons are strongly bound, and in this kind of a system, this is a porphyrin, this is a phthalocyanin. A lot of pi electrons are there, which means they can be easily polarized when you put in a laser light, because of which you see a strong nonlinearity. M is the central metal ion, and this is a periphery. You can have different attachments at the periphery. So the idea is with these kind of materials, you can model them, you can design them with different metals, you can design them with different peripheral groups. You can look at various scenarios and how the nonlinearity is varying. This is what we call as 4 pyrrole links here, linked by the methane carbon bridges. 4 indole units, pyrrole rings linked by the nitrogen atoms conjugated with benzene rings. So typically, if you look at this kind of molecules, they have two absorption bands, one in the UV 200 to 400 called the B band, and one in the 600 to 800, which is the Q band. That's the biological window. There's a lot of biological applications like photodynamic therapy have been looked upon. So this is how the electron system, electron cloud, if you look at it, this is how the electron cloud is. When you put in an electric field, the cloud gets disturbed, and then you create this dipole moment, and that results in the nonlinear process. And there are also other processes like electron transfer, energy transfer from the core to the peripheral, or from the peripheral to the core. So all these processes will give rise to variety of nonlinear optical properties. So we started with why they are interested. It's interested because we can choose the electronic properties. We can change the distance between these electronic levels. Different metal ions. We can in fact put about 70 metal ions in this one. So theoretically 70 metal ions can be put, so you get 70 different samples. The greater is the conjugation, this pi conjugation is what I told you. Pi electrons are there. They respond very fast to the external laser field. That gives rise to optical limiting effects. So large, ultra-fast nonlinear response, broadband tunable response, ultra-fast recovery time, large optical damage, thermal damage threshold, good chemical mechanical stability, and it's very easy to synthesize them, change them. So as I said, when you have such a system, these are your singlet state S0, S1, S2, T0, T1, or the T1, T2, or the triplet state. You have variety of transitions occurring depending on what is the energy you're putting in, which matches with this transition or this transition. And once it comes down, it can come down to internal conversion, fluorescence, phosphorescence, intersystem crossing, reverse intersystem crossing. Then you can also have delayed fluorescence. A huge amount of processes can take place in this kind of materials. So I'll skip this again. These are formulas well known to many of you. So you can design with alpha n. You can have only 2 alpha 2 is 2 photon absorption. If you have alpha 3, 3 photon absorption, you can have alpha 4 also, and you can get sigma is the cross section here. Alpha is the coefficient, analog coefficient. So you can have, depending on the nonlinear absorption process, you can have many number of processes. So some materials, for example, you see this is one phthalocyanin with different peripheral groups with no metal inside. Then you have a zinc metal here, but with the same peripheral groups with the zinc metal. So no metal and zinc. And in this case, there is a zinc metal, but the peripheral constituents are different. So when these things are designed and produced in the lab, you get different absorption properties and emission properties. So when you change absorption emission properties, your nonlinear properties will change. This, for example, the nanosecond optical nanosecond Z-scan data of both these phthalocyanins. When you go to femtosecond, you see nanosecond, all you see is only reverse saturative absorption, because these are long pulses, so they remain in the excited state for a long time. But when you go to femtosecond pulses, you see the saturative absorption, then going back to reverse saturative, and then there is a switching off for this nonlinear absorption. So this kind of mechanism is possible in these materials. You can also see the opposite of this, where you start with the reverse saturable, then there is saturation. So instead of a M kind of a curve, you get a W kind of a curve. So all these are possible in these materials. So we did both nanosecond and femtosecond. And in femtosecond, you see this is 3-photon absorption. This dotted line is a 2-photon absorption. So depending on the pulse duration and where you're exciting, nanosecond you excite at 532, femtosecond at 800. So 800 gives rise to 3-photon absorption in this material, same material, but with femtosecond pulse. So you can see that we have done for both alkoxy and alkyl thiocyanins at 532 nanometers. We see that one of them gives you a much stronger nonlinearity compared to the other. So we try to correlate this kind of performance with respect to the actual structure. You can also do the DFW measurements and see how fast is the nonlinearity. Okay, these are the, as I said, alpha 3, 3-photon absorption we observed with the femtosecond pulse, 2-photon with the nanosecond pulse. This is in form of a thin film. See, any material you want to look for a device application, then you need to do it in form of thin film or in glasses, so that they actually be used rather than claiming that we only found a material which has a strong nonlinearity. We can also make nanoparticles out of this, for example, and we have seen that when you make nanoparticles compared to the bulk, these nanoparticles had a strong nonlinearity compared to the bulk nonlinearity. These materials will have different properties depending on the solvent. In case of chloroform or water, their absorption properties will change. So this will indirectly affect the nonlinear properties. Another set of thiocyanins which we have studied, these are called zinc thiocyanins. These are made by my colleague Giri Babu at ISCT. And we have done a series of spectrochemistry studies, looked at the absorption, emission in different solvents. Usually they have, some of them are emitting, they have emission lifetimes of few nanoseconds. For example, this is what we are showing, a nanosecond fluorescence coming from these molecules. And then we did a series of picosecond Z-scan studies at different wavelengths by tuning the wavelength 640, 680, 700 nanometers for first molecule and second molecule. You can see depending on the wavelength, there is saturation and then suddenly it switches to RSC. Similarly, for this, it starts with reverse saturation, then goes to saturation and then RSC. So wavelength plays a very important role in this process. Intensity plays a very important role. The concentration plays a very important role. All needs to be considered when you are analyzing the data. These are some of the values you can see. Large 2-photon cross-section values. These are always measured in Gopart-Mayer units, GM units, to get large sigma 2 values for these PC2 molecule, whereas PC1 did not show sigma 2, it was showing only saturation absorption. Saturation absorption has applications in Q switching. That's a totally new, different area, and huge amount of work is being done in that. So summary of all those things, we found the thin films better than the bulk, nanoparticles better than the bulk, and metal thiocyanins were better than the free-base thiocyanins. Then axial substitution effectively decreased the aggregation phenomena so that you get more stability. So all these correlation were done using this particular data. Another set of molecules we studied are called porphysines, where you have these naphthalene moieties at the end. Because of this naphthalene moieties, what you see is an extra absorption peak here. These are normal like your porphyrin or thiocyanins. You see two peaks, B band and the Q band. But this naphthalene gives you another band here that gave us two interesting properties. When you pump with lower intensities, we saw 2-photon absorption. When you pump with higher intensities, we saw 3-photon absorption. So the blue dotted line is a 2-photon absorption. So this for 5 different porphysines. So 2-photon at lower peak intensities, 3-photon at higher peak intensities. This is what happens when you have strong intensities, then the transitions can go from here to this particular band, which is because of the naphthalene. So there is an energy level where this population go and stays here. When you put only low intensities, it goes into this level. So at higher intensities, you can see strong 3-photon. At lower intensities, you can see strong 2-photon absorption. These are the 2-photon cross sections. Again, very strong 2-photon cross sections. However, these are made with the picosecond pulses. So when you go to femtosecond, probably these numbers will slightly come down. These are the cross sections. Sigma 3 is a 3-photon absorption cross section. We also looked at how fast these are states are coming down. Some Prof studies were done. So we calculated what are the lifetimes of each of these states. And then this clearly tells us this is because of the naphthalene group. This is because of the porphyrin. So when you excite it here, there can be various transitions. So this is tau 3 we define, tau 2, this is tau 1. tau 2, tau 1 when you are using a 800 nanometer photon or a 600 nanometer photon. So a detailed study was done to understand how the absorption takes place, how the nonlinear absorption takes place, how the various states relax back to the ground state. This is very important when you talk of devices. Another phthalocyanine, when you compare porphyrin and a phthalocyanine, we have done again detailed studies. I hope I have some more time. And skip this part. So here we see that, for example, this is done with a megahertz pulse. Therefore, what you see is a strong nonlinear absorption and therefore a strong sigma 2 in terms of 10 power 7 GM. Where you see in this case, this is for the phthalocyanine, this is for the porphyrin. You can see this is much higher, 70 in case of 700 and phthalocyanine, 1.8 in the case of porphyrin. So you can choose your molecule depending on your application. You can also see N2 varies with the again with the kind of thing. All of them have negative. Again, in this case, N2 is stronger in this case at 700 for phthalocyanine compared to porphyrin. Another set of phthalocyanins called carbazole substituted phthalocyanins, a very interesting molecule where we've done two molecules in this case. This is absorption emission studies. And a detailed study we have done as a function of wavelength, 700, 800 nanometer, both in the megahertz pulse as well as kilohertz pulse we have done. We wanted to see how the pulse duration is affecting the nonlinearity. Both kilohertz, this is a kilohertz pulse, this is a megahertz pulse, this is for the first molecule, this is for the second molecule. Detailed studies we've shown that, for example, you see these are very large numbers for the kilohertz pulses. This is much stronger numbers compared to this. So this CBCPC2 is weaker compared to CBCPC1 in terms of kilohertz excitation. So we can do a complete detailed analysis and come out with pointers as to which molecule will be useful for optical emitting, which molecule will be used for imaging applications. Suppose if it has satural absorption, which molecule is used for Q switching kind of applications. Again, we did a lot of excitation studies to understand how these molecules go to the excited state, come back to the ground state, how fast are they, how long the population stays in each one of these states. Similar, another zinc phthalocyanine molecule, I'll skip this. We've done a lot of studies on this. In this case, what we have done is we have gone to the near IR wavelengths, 1 micron, 1.2 micron, 1.3, 1.4, 1.5 micron. So the more you go into the infrared region, then for the same band gap, you need more number of photons to go into the excited state. Therefore, what you see here is for higher wavelengths, you start seeing 3 photon absorption. For even higher wavelengths, you start seeing 4 photon absorption. Because these are short laser pulses, there is sufficient intensity in these pulses. You can observe these higher order nonlinear absorption process, 4 photon absorption. If you go into 2 micron, you can still see 5 photon, but because of our limitations in our laser source, we could not study those things. So you start with 2 photon, go to 3 photon, then 4 photon. You can go further also. I'll skip this dynamics part. We completely analyze how these dynamics occur. Then there's another very interesting molecule, imidazole substituted molecule, where you have these 4 peripheral substituents here. And in the central, we have a zinc or a copper molecule. There is a space a bit. Yes?
Can we have another 5 minutes for you?
10 minutes, I'll finish. Sorry. I'll finish it. So this is absorption emission properties. And again, we've got very good sigma 2 photon cross section. This is with a pure femtosecond pulse and kilohertz pulses. So there's no question of thermal nonlinearity here. These are all electronic nonlinearities when we talk about 50 femtosecond and 1 kilohertz pulses. So these are really strong 2 photon absorption. This will be useful when you do imaging applications. I'll skip the dynamics part, complete details. Then another set of porphyrins. In this case, this band is weaker compared to this band. The B band is much stronger and the Q band is weaker in this kind of molecules. Again, we have done a series of studies using femtosecond pulses. And what we see is a very strong nonlinear absorption. In this case, thousands of GM, hundreds of GM we can observe. I'll skip this part. There are another set of molecules called corals. They are slightly better compared to the porphyrins because they have stronger fluorescence, therefore they are used in biomedical applications. They have better catalytic properties and therefore they can be used for what we call as photodynamic therapy. All these molecules are very good for photodynamic therapy. And they can also be used for microscopic applications and optical limiting applications. These are the two sets of corals we did, one with the phosphorus and one with the free base. I'll skip the structure part. I'll go to the NLO part. So we have done at both 800 and 600 nanometers, and we have seen that about 190 and 180 is a two-photon absorption cross-section. Again, when we do these studies, we get alpha 2, we get alpha 2, we get N2, we get real part, imaginary part, and the total chi-square. So we evaluate the complete NLO, and we can also compare with the actual DFW. As I said, DFW will give you the total magnitude. We get the total magnitude from this also. We can compare and see both of them match very well. But this tells you when you, this is what I'm plotting is time versus the DFWM signal. How fast is the signal decaying? That will tell you how fast is the response of that nonlinearity. So this is additional advantage of DFWM. Whereas DFWM will not tell you how much is a real part and imaginary part. It will only tell you mod chi-square, modulus of chi it will tell you. It will not tell you how much is real imaginary part. This will tell you that. Another set of corals, detailed studies again. So I'll try to wind up. Even if you take a normal molecule like rhodamine B, this has again, it's an organic molecule. It has exotic properties. So we have done a series of studies by changing. This is how the absorption spectra looks like. That's why it is used in the laser dye. 532 is strong absorption. We pumped at 435, 532, and 600, which is the edge of the absorption. 400, there's no absorption. So we can, as I said, we can 5-level modeling we can do. We can actually fit the Z-scan data to this using this. What you start seeing is at lower concentration, if the saturation at higher concentration, then suddenly it starts switching to the RSC behavior. Beautiful. For the same peak intensity, you can see the change of concentration going from RSA to the switching behavior to the SA. So for the same molecule, depending on the concentration for a particular intensity, one can achieve a different kind of nonlinear optical mechanism. See another molecule, malazite green, where we have seen this kind of behavior as a function of intensity and as a function of concentration, as a function of wavelength here from 700 RSC, 750 you see SA RSC, 800, and at 1000 it is complete RSC. So we modify the 3D part of it. You can look at our paper here. So we write down this in terms of linear absorption, high saturation, saturable absorption, two-photon absorption, then three-photon absorption. So all three are incorporated. Only then your data will be able to fit nicely for each of these wavelengths. We can also prepare nanoparticles. We prepare nanoparticles in our lab using simple laser ablation. I'm not going into the details. So in this case, I'm showing you TiO2 nanoparticles and Ag attached to the TiO2 nanoparticles. So you can see in this case, Ti and Ag, both of them, oxygen, titanium, and Ag. So we confirm that these are really TiO2 nanoparticles. And you can do both, this is for the kilohertz studies, and this is for the different wavelength region up to 1.2 micron. So detailed studies were done. And what we have seen is there is a transfer of energy occurring from the TiO2, which is a more or less like a semiconductor or close to insulator. There is transfer of energy occurring, and because of which there is a strong nonlinear absorption in the presence of TiO2 and silver. So if you look at the table, this is three-photon absorption. This pure TiO2 nanoparticles. This is for the AgTiO2 nanoparticles. Your three-photon absorption coefficient changes when you put in your silver in the TiO2 nanoparticles. So we try to understand the role of TiO2 and Ag in these nanoparticles. Another set of molecules we have done. I'll skip this part. Detailed studies were done. We have also done in form of a thin film. See, these are megahertz studies. These are kilohertz megahertz studies. These are kilohertz studies. These are thin film studies. So we try to compare which one will be useful for a particular application. Another set of bimetallic colloids or trimetallic colloids. I'll skip this part. We also done some based on graphene oxide, quantum dots, silver doped, gold doped, silver gold doped, and we try to see if we can improve the nonlinearity or improve the nonlinear absorption. This is graphene oxide, gold, presence of silver, and presence of alloys here. And we have seen that nonlinear absorption changes drastically. As a function of intensity, it goes from saturation to reverse saturation and in between M kind of a behavior. And we try to explain in terms of the energy level diagram. So you see that graphene oxide N2 and for doped graphene oxide, the nonlinearity changes drastically. It changes by about 5 times in this case. Our own case, we have studied perovskite nanocrystals, a strong area, very hot area now. We have chemistry colleagues who prepare these nanocrystals, nanocubes, nanorods. So changing the size of the nanomaterial changes the nonlinearity, changing the morphology changes the nonlinearity. So we have studied in terms of rods and cubes how the nonlinearity varies. In terms of solution, in terms of film, how the nonlinearity varies. So a series of studies were done varying from 500 nanometer to up to 1 micron. We have studied, I've skipped some of these. And what we have seen is, in some cases, we have seen 2-photon absorption. But when you go to higher wavelengths, we start seeing 3-photon absorption and 4-photon absorption. As I said, linear absorption plays a very important role. So we can find out from 500 to 1500, we can see 2-photon absorption in this case, 3-photon absorption up to 1200, and 4-photon absorption in the case of 1300 to 1500 nanometers. These are non-fluorescent nanocrystals. These are fluorescent nanocrystals. So we can compare and then come to a conclusion which one of them performs better. Another set of crystals. In this case, there is only nickel doping in this nanocrystal. So I'll skip this part. This is 400 nanometer data. The earlier one was 800 nanometer data. These are some of the works which we did with Sabari long back. He prepared this beautiful RGO nanocomposites doped with cadmium Fe2O4 and AU Fe2O3. And we have seen again a variety of nonlinear absorption behavior in this and good optical limiting behavior. In some cases, we also see nonlinear absorption switching also. There are sets of glasses are very important class of materials because of various advantages, and we can also have variety of glasses, metal oxides. You can dope rare earth, you can make transition metal oxide, you can make dope metal nanoparticle into glasses. So problem is it's low nonlinearity. As such, glass has low nonlinearity, but by doing these modifications, we can improve the nonlinearity. A series of studies we did in borate glasses, lead borate glasses. Skip some of them. This is for example, sodium borate oxide glasses. We see what is the effect of antimony in this one, how the antimony affects the nonlinearity, how the gold nanoparticles affect the glasses, alkali borate glasses. In this case, europium is doped, and then different amount of gold is put in. Again, we did a series of studies. A lot of new glasses were prepared and studied. So as I said, depending on your absorption, the nonlinear absorption, for example, this work by this gentleman, this is chalcogenide glass, and what they show is they show 11 photon absorption, starting from 2 photon, 3, 4, 5, 6, 7, 8, 9, 10, 11 photon absorption. They see this is 1.9 micron, 4 photon absorption, 2.4 micron, 5 photon, 3.78 photon, 4.2 micron, 9 photon, and 5.1 micron. This you get only through an OPA. 11 photon absorption, 5.6 micron, they did not see any absorption here. So therefore, people have observed 11 photon absorption also in these molecules. These are crystals, gallium phosphide, normal crystals, zinc selenide, gallium selenide, zinc germanium phosphide. The people studied the mid-infrared nonlinearity. So people go to 1 micron, 2 micron, 3 micron, 4 microns with short laser pulses, and then they show this, for example, gallium phosphide cut. This is a crystalline direction. So multiphoton order is this is theoretically so 6, experimentally also it shows 6, 4, 5, 6. So they show all this multiphoton absorption in these nonlinear materials. People also have done the terahertz Z scan. For example, this group studied the Robert Boyd group, water vapor, and then they did the terahertz Z scan and then tried to understand. Another group which studied terahertz nonlinearities in indium gallium arsenide. This is how the terahertz Z scan looks like, more of it is saturable absorption. Another group which studied in indium end-op semiconductors. So this is very difficult experiments for aligning such setups. It's not easy. 1 second. I'll wind up. This is our own group, Ravindra Kumar at TFR. They generated huge amount of terahertz radiation in water, and then they used that to study the nonlinear absorption of silicon, where they show that there's saturated absorption at the terahertz frequencies of 3 terahertz or 2.5 terahertz. Supercontinuum, I'll skip some part. Another way to achieve broadband light, people have achieved the 1 to 4.5 microns, 1.8 to 4 microns by changing the material, different materials. 2 to 6 microns in a silicon nanowire, small material, people have achieved supercontinuum generation, photonic crystal fibers. So as I said, for mechanisms contributing to N2, heating will give you a very large N2, but a very slow one. Electronic nonlinearity gives you a small magnitude, but very fast. So when you talk of all optical switching, people talk of picowatt or femtowatt required to switch from one state to the other state, 0 to 1 or 1. I will show you one example. This is, for example, a directional coupler, right? So you have light coming in and light coming out. So you want to, this is one state. And then when you put in a strong field, now light will go and, I'm finishing. So light comes out here. This is called the on state or the off state. So this has to be done at very low powers. So people have now made materials, lithium niobate based material, which talk of extremely fast optical switching at very extremely low energies. So they use second order nonlinearity, and then they use only femtojoules, and time response is 46 femtoseconds. So these are the materials which will be used in future communication devices. New materials which are called epsilon near zero, epsilon becomes more or less zero at that particular wavelength. Multiphoton absorption, protein fibers, a variety of materials. Probably we'll hear a little bit in the evening about this. Then you have applications in new frequency generation, pulsing, micro machining, a huge area of nonlinear optics, spectroscopy, telecommunication applications, sensors, data storage, signal processing, a variety of applications one can think of. Terahertz generation for sensing, we do a little bit of. So I do not have time to go into this, so I'll skip this part. There are many applications of nonlinear optics in day-to-day life, right? New materials are being discovered. For example, this group, Mark Humphrey group at ANU, does beautiful work on nonlinear absorption, multiphoton absorption, where they design new molecules with very strong 2, 3, 4, 5 photon absorption materials. Last but not least, when you do measurements, you always do in solvent. So one needs to consider the effect of solvent also. So this paper nicely summarizes what is the effect of the solvent, what is the magnitude of the solvent when you do measurements. So they clearly tell you all the common solvents, and as a function of pulse duration, what is the value of N2. So when you are doing in solution, you need to subtract the value of the solvent. Only then you get the actual solute value. So this paper summarizes all the magnitudes of various solvents with different pulse durations, and these are very accurate numbers, very useful numbers. So with this, I'll stop here. I've exceeded my time. Sorry for that, and I hope you have got a flavor of different mechanisms which can lead to nonlinearity, different materials which have been studied for nonlinearity, and many applications resulting from this nonlinearity. So